Hello everyone. In this lecture, I shall discuss the differential equations. Okay, so this differential equation, here I will discuss basically the introduction and various definitions involved to study the differential equations and the formulation of the differential equations. So basically differential equation is one of the most important aspects to study the applied mathematics. Now suppose you think of a physical situations, okay, the physical system, the behavior of the physical system can be best understood by mathematical modeling. Okay, by mathematical modeling, right? What is mathematical modeling? Means we relate the variables by one or more equations, right? Now once the physical system is under motion, right, then there will be the case of your rate of change of the system, right, rate of change, and it leads to the derivatives. See, if the equation involves the derivatives or the differential coefficients, then it leads to a differential equation, right? Most importantly, in science and engineering, you think of some applications oriented problems, you say the laws of natural growth, right, radioactive decay, radioactive growth, Newton's law of cooling, law of thermodynamics, electric circuits, etc. When transformed into mathematical forms, it yields the differential equation, right? It leads to the differential equation. So to discuss the basic definitions involved in this differential equations and the further details, let me to introduce myself. Professor Susanta Kumar Paikray, currently working as a professor in the Department of Mathematics, Veer Surendra University of Technology, Burla, Odisha, India. So without much delay, let us now start the basics thing of the differential equations. If you think of a function, you say, suppose you are given a function y is equal to f of x, right? And suppose another function is given to you, is z is equal to f of xy here, right? In first case, your y is a dependent variable here, and x is an independent variable here, so here only one independent variable, here. Now here z is a dependent variable here, and here x and y are the independent variables here, right? Now in first case, we find the ordinary derivatives. What is your dy by dx? Now in first case, if we differentiate the dependent variable with respect to the independent variable, we get dy by dx, or we call it y dash, we call it y dot, or it is my f dash, like this. So these are all called the differential coefficients, okay, differential coefficient. And similarly, if I find the second derivative, d square y by dx square, this is my y double dash or y double dot, so on. So these are also my differential coefficient of second order, right? Differential coefficient of order 2 here, and here order 1 here. Now here simply dy, simply dx, these are called the differentials. Likewise, here I find zx, this is my del z by del x or del f by del x, or I write it fx, right? And similarly here zy is here del z by del y, and zxx is here del square z by del x square, and here zxy is del square z by del x del y, and similarly here zyy is del square z by del y square. So these are the partial differential coefficients, okay, these are the differential coefficients, these are partial, right? This leads to the partial derivatives. Here y is treated as constant here x is treated as a constant here, right? So in partial differential equations, we have the independent variables more than one, right? More than one independent variable, right? But here in ordinary differential equation, we have only one dependent variable, one independent variable. In both the cases, the dependent variable is 1. Here only one dependent variable and the dependent variable is 1, right? In ordinary differential equation, the independent variable is 1. In partial differential equation, the number of independent variables are more than 1. So now coming to the definition of the differential equation. Moreover, some notational sake, we denote it P as Zx and Q as Zy and R as Zxs, S Zxy and T Zyy. Okay, these are some standard notations. Now let me to discuss some basic definitions. Coming to the definition of differential equation, we have, so coming to the definition, an equation involving the derivative of dependent variable with respect to independent variable. Okay, so we may write it here. So the dependent variable in each case is 1, only one dependent variable. Here only one dependent variable in any case, but the involving the derivative may be more than one derivative, y dash, y double dash, so on. And with respect to the independent variables, right, we may have variable or variables. If it is partial, it leads to more than one independent variable. So we write an equation involving the derivatives of dependent variable with respect to independent variable or variables, or the differentials also, right? If this dy present, dx present, or the differentials is called a equation. It's known as it's called the differential equations. Okay, differential equation. Now this differential equation are of two types. The differential equation are of two types, ODE and PDE, ordinary differential equation. We call it ODE, and partial differential equation we call it PDE. So in ordinary differential equation, we have one dependent variable, right? One dependent variable and one independent variable and differential coefficient of dependent variable with respect to independent variable. And in partial differential equation, right, in partial differential equation, one dependent variable, right, two or more independent variables, and differential coefficient of dependent variable with respect to independent variables, right? Independent variables, right? So this is what the definition of PDE, and this is what the definition of ODE. So let me to write in details. So thus coming to the definition of ordinary differential equation, a differential equation involving derivatives of an independent variable, always the independent of a dependent variable. Okay, dependent variable is only one with respect to only one independent variable, right? Or instead of the derivatives, if you have the differentials dy dx, then also okay, is known as an ordinary differential equation, right? In general, I may write it, the ordinary differential equation, I may write it involves your x, it involves your y dash, y double dash, it may also involve the nth derivative, right? So this is equal to 0. In particular, if I say y double dash minus 5y dash plus 6y is equal to 0, this is the ordinary differential equation. If I write d square y by dx square plus dy by dx whole cube is equal to 0, this is also a ordinary differential equation. These are the example of the ODE. So likewise, in partial differential equation, it involves always the dependent variable is one, n dependent variable, where two or more independent variables. Okay, a differential equation involving derivatives of an dependent variable with respect to two or more independent variables is known as an PDE, is known as a partial differential equation. So here if I write it in general, this can be written as a function of, if I take the dependent variable as z, independent and x, y, then there may be del y by del x, then there may be del z by del x, del z by del y, right? Del square z by del x del y, so on, as I have told you, p, q, r, s, t, so on, right? So that maybe I can write it, or z, x, y, p, q, r, s, t. Okay, so this thing is equal to 0. So this is the general form of a partial differential equation. If I write it, utt is equal to c square uxx. So here u is a function of ux and t, right? One dependent variable and two independent variable here, and one dependent variable, and I write it utt is equal to c square uxx. If I write x ux plus y uy is equal to 0, this is also a PDE. Del square u by del x square plus del square u by del y square is equal to 0. This is also an PDE. These are the example of the PDE. So I think the definition is clear. In both the cases, there is only one dependent variable. In ODE, there is exactly one independent variable, and the derivatives of dependent variable with respect to independent variable. But in PDE, there are two or more independent variables and the differential coefficient of the dependent variable with respect to two or more independent variables. Okay, so this is the definition of ODE and PDE. Now let us discuss the order and degree. Now coming to the most important definitions, order and degree of a differential equation. The order of a differential equation is the order of the highest order derivative present in the differential equation. Next, coming to the degree. The degree of a differential equation. Is the highest power. That power must be positive integral power. Okay, positive integral power. It must be a positive integer. The highest positive integral power of the highest order derivative provided the equation is made free from radical signs and fractional powers as far as the derivative terms are concerned. That means to say, it must be the highest integral power of the highest order derivative, provided we have to made free wherever the differential derivative terms are there. It should be free from the radical sign and the power should be free from the fractions. Okay, moreover we say, moreover it must be a polynomial equation in derivatives. in derivatives. Okay, so now coming to some examples. Suppose I have a differential equation dy by dx plus sine dy by dx is equal to 0. You see, it is not polynomial in y dash, not a polynomial equation in y dash, because it is a derivative term here. Okay, y dash. So degree is not defined. However, order is fine, because the power is 1 here. The order is 1. Okay, order is 1 here. Suppose coming to one more example. Suppose you have dy by dx whole square plus dy by dx minus sine square y is equal to 0. You see, it is not a polynomial in y, not a polynomial in y, but we need polynomial in derivatives, but it is polynomial in derivatives, right? However, polynomial in y dash. Okay, so degree. So here this is the order here. This is the order of the derivative here. Okay, this is the order of the derivative here. The order of the derivative is 1 here, and the order is 1 here. Okay, order is equal to 1 here, and this is for your order, and this is for your degree, right? The power of the highest order derivative, and the degree is equal to 2 here. In the previous example, this is your order. Okay, this is your order, and this degree is not defined. Since it is not a polynomial equation, the degree is not defined. Okay, now coming to some more examples. So coming to some more examples. Suppose you have dy by dt whole cube is dy by dt whole square plus 3 root over. You see, there is a radical power here, radical sign here, is not it? This is a radical sign over the derivative term. So we have to make free it. Okay, so what we have to do? We just make whole square in both sides. Dy by dt whole to the power 6 is dy by dt whole square plus 3. Okay, so now we are ready to find the order. So the highest order derivative is 1 here, so this is the order, and this power here is degree. Okay, this is the power here is 2, the power here is 6, so this is the highest positive integral power. This will give our degree. So order is here 1 and degree is here 6. Coming to some more examples. So coming to one more example, here dy by dx is y plus x divided by dy by dx. You see here. So here you see, so this is the derivative term is present in the numerator. If I bring into the numerator, then the power will be minus 1. We have to remove it. Okay, so we just simplify it first. Okay, we make this denominator free. So this is dy by dx whole square is y dy by dx plus my x. Now the order is 1 here. Highest order derivative is, the order is 1, and the power here is, highest power is 2. So order is equal to 1, degree is equal to 2. Coming to one more example. Now coming to this example. So this will give me highest order derivative, this will give me the order. But you see, here there is a fraction here. Here also there is a fraction. Right, this power should be positive integer, and this should be free from the derivative. Okay, so the denominator is 3 here, the denominator is 2 here. So the LCM of 2 and 3 here, LCM of 2 and 3 is 6. If I take the power 6 here, so what I have to do is dy by dx to the power half whole to the power 6 is minus d square y by dx square, this to the power 2 by 3 whole to the power 6. Okay, Now this 3 and this 2 cancelled here. So now this 2 and this cancelled here. Now this is the highest power. Okay, this is the highest power. So this will give me the order, and now this power becomes here 2 into 2 4. Okay, so that is my, so this is my dy by dx to the power 3 is equal to d square y by dx square to the power 4. Now we are ready to find the order and degree. This is my order and this is my degree. Order is equal to my 2, degree is equal to my 4. Coming to one more example, y triple dash plus y dash square plus e to the power y dash is equal to 0. You see here. So this is giving us the order. Order is 3 here. Okay, but for the degree we see this is not a polynomial in derivatives. Because of this, not a polynomial in derivative. Okay, in y dash. So degree is undefined. Degree is undefined. Now coming to one more equation. Suppose x square del square u by del x square whole to the power 2 plus y square del square u by del y square whole to the power 3 is equal to 0. You see the highest order derivative here is, this is also highest order derivative, this is also highest order derivative. The order is 2, order is equal to 2. Now we have to see this power is 2 here, but this power is 3. This is the highest positive integral power. So this will give us the degree. The degree is equal to 3 here. Okay, in this way we will able to find the order and degree of a differential equation. Now coming to the solution of a differential equation. The solution, or we call it a integral, or we call it the primitive of a differential equation, is a relation between the variables involved in the equation which satisfy the differential equation, which satisfy the differential equation. Okay, or we can say any function satisfying the differential equation is known as the solution of a differential equation. Right, for example, suppose you are given y double dash minus 5y dash plus 6y is equal to 0 is a differential equation. What is the order? The order is 2 here, the degree is 1 here. Okay, so what is its solution? If I put y is equal to e to the power 2x, right, and I find y dash and I find y double dash and I substitute over here. Okay, so this is a function, or this is a relation between the variable involved. Okay, so it will satisfy this equation, right? So this is a solution. This is a solution of, let it be my equation 1 of equation 1. Similarly, if I say y is equal to 3x, y is equal to e to the power 3x also. If I find y dash, if I find y double dash and I substitute all this thing here, this will again also satisfy, is also a solution, of equation 1. If I merge these two, okay, if I merge these two, y is equal to e to the power 2x, some constant times this plus some another constant time e to the power 3x, this is also a solution. Okay, because if I substitute it here, if I find y dash, if I find y double dash and I substitute it 1, then 1 will satisfy, is also a solution, Now the beauty of this solution here is that, so here the order of the equation is 2, right, and the number of the arbitrary constant is 2. And this solution here is called a general solution, right, general solution. So what is a solution? The solution of a differential equation is a relation between the variable involved. Okay, in this equation the variable involves y dash x means it is here x y dash y double dash. Okay, so now the relation between x and y, So this is a relation or this is a function. It will satisfy these equations. Now here, if the solution involves the number of arbitrary constants is same as the order of the equation, then it is called a general solution. Now coming to the general solution, or what we call the complete solution. A solution involving the number of arbitrary constants is equal to the order of the differential equation, is equal to the order of the differential equation is known as the general or complete solution of the equation, of the differential equation. Okay, as I have told that this is the general solution because it involves two arbitrary constants which is same as the order of the equation. Now coming to the particular solution. If the particular value of the constants are involved, right, then it is called a particular solution. So as you know, the general solution involves the number of arbitrary constant is equal to or same as the order of the equation. Now coming to the particular solution, if we able to get the particular value to these arbitrary constants, okay, so the definition is like this: the particular solution of a differential equation is the solution which is obtained from the general solution by assigning particular values to the arbitrary constants. So how these particular values can be assigned? Based on certain condition. So these are based on certain conditions. Okay, these conditions may be initial condition or boundary conditions, and it leads to the IVP or BVP. Right, IVP means initial value problem, right, and BVP means boundary value problem. So in initial value problem some conditions are there, initial conditions are, in boundary value problem the boundary conditions are there. So these conditions are substituted over the final solutions, general solution, then this will yield the arbitrary constants. So now coming to the IVP and BVP, the initial or boundary value problem is one in which the solution to a differential equation is obtained subject to the conditions on the unknown function and oblique or its derivatives, okay, specified at one point or two or more values of the independent variable. Okay, such conditions are called initial or boundary conditions. The differential equation with initial condition is called IVP, with boundary condition is called BVP. In particular, coming to an initial value problem, IVP, initial value problem, so it may be of first order or second order. Suppose my type 1, this is dy by dx is equal to f of xy. So here it is the order is 1 here, so we need only one condition, y of x0 is equal to y0. So this is the initial point here, right, of the independent variable. Now if it is of type 2, if it is second order, d square y by dx square is f of xy and dy by dx. Here we need two conditions. Okay, initial conditions means y of x0 is equal to y0 and y dash of x0 is equal to some y1. You see here, this is x0, this is x0. These two values are same. Okay, this is why it is called initial condition. Right, means these two values are same here. But in BVP, these values are two different. One is initial value, other one is boundary value. Now coming to the BVP, boundary value problem, we have basically it is a second order differential equation or higher order differential equation. Y double dash is equal to f x y and y dash, right, which satisfy one of the conditions such that there may be condition may be like this: y of x0 is equal to a and y of x1 is equal to b. You see, this condition and this condition are different, right, but here you see this condition and this condition are same in IVP. Or in 2i it may be y of x0 is equal to alpha and y1 of y dash of x1 is equal to alpha beta. In any mean, you see, this is x0 and this is your x1. Okay, right, it is y and it is y dash, no issue. Now coming to the third one, it is y dash x0 is equal to some theta and y dash x1 is equal to some zeta. Okay, in that way. But in each case we have to see these conditions are different, right? This is different from this. This is the comparison between the IVP and BVP. So in IVP, this value of the independent variable are same. In BVP, the value of the independent variable are different. One is for initial and other one is for the boundary. Coming to another important solution is the singular solution. Also it is called unusual solution or odd solution. Means, so what is the definition? A singular solution of a differential equation is the solution which cannot be obtained from the general solution. Okay, so that means since it cannot be obtained from the general solution, right? That's why it is called a unusual solution or odd solution, or it is a singular solution. For example, if we have a differential equation y dash square minus xy dash plus y is equal to 0, what is the order? The order is equal to 1. If we check that y is equal to cx minus c square, you check it, right? You check, and it must be how many arbitrary constant? Only one arbitrary constant, c. Okay, is a general solution here. This is a general solution. However, I have another solution. Y is equal to x square by 4. Okay, y is equal to x square by 4. If you substitute it, you find y dash and substitute it. Okay, it is 2x by 4 is x by 2, and you substitute it, then your 1 will satisfy. Okay, then equation 1 will satisfy. However, you see, this cannot be obtained from this. Okay, it cannot be obtained from this. Cannot be obtained from general solution, right? Cannot be obtained from the general solution. That's why this is called a singular solution. Okay, this is called a singular solution. So how these singular solutions are basically obtained? Okay, while we know how to find the solutions, we'll see that this is a solution. Now how this singular solution is obtained? Now the question is how to get the singular solution. Okay, so what to do? We just consider the given equation. Let it be your f. Let your f is the given equation y dash square minus xy dash plus y is equal to 0. Now setting as let my y dash is my p. So it is my p square minus xp plus y is equal to 0. Okay, so now let it be my equation 1. Now you find fp, del f by del p, you find the partial derivative. It is 2p minus x is equal to 0. So this implies my x is equal to p by 2. Now I solve this, solving I and 2i. Now eliminating p between I and 2i, right? What we get? That means if I substitute 2i in I will get p square by 4 minus this is your p is equal to x by 2. This is equal to your p is equal to your x by 2. Okay, so this implies p is equal to your x by 2. This is my equation 2i. So now if I substitute it in 1, what I get? From 1 I will get, right? From 1. So now from your substituting this here, I will get x square by 4 minus x square by 2 plus y is equal to 0. So that means minus of x square by 4 plus y is equal to 0. So that means y is equal to x square by 4. So this is a singular solutions. It has no relations with the general solutions. By substituting, rearranging it for any c, I cannot get it. Okay, that's why it is called a singular solution. Now the formulation of a differential equation. Okay, what are the working rule? Step 1, you consider the given equation. Consider the given equation. That means the solution here is like this: x, y, the constants a, b, like this, these are present. Okay, suppose this is the given equations. From this equation we have to see what is the differential equation for which this is the solution. Now we have to check how many constants are there. Okay, so let it be my equation 1. Let it be my equation 1. Now in step 2, differentiate with respect to x. Differentiate with respect to x successively as many times as the number of constants. Okay, if there are 2 constants, we have to find y dash, y double dash. 3 constants, we have to find y dash, y double dash, and y triple dash. And step 3, okay, so here we find y dash, y double dash, y triple dash. Suppose another constant is c, like that. This is my 2i. Now we have to eliminate the constants. Okay, now eliminate the arbitrary constants a, b, c, etc. in between I and 2i to get the desired differential equations. If I solve one example, then your idea will clear. Now consider one example. You are asked to find the differential equations from the given curves, family of curves. Family means why it is family of curve? Because for a and b, different value of a and b will generate different curve. Okay, here a and b are arbitrary constants. So there are 2 arbitrary constants. So the differential equations must be of order 2, right? So solution 1, let my y is equal to a to the power x plus b to the power minus x plus x square. So I need to differentiate twice because 2 constants. So y dash is a to the power x minus b to the power minus x plus 2x. And I find the second derivative, y double dash is a to the power x minus plus b to the power minus x plus 2. Now you see, if I subtract y minus y double dash, okay, now y minus y double dash, then this and this will cancel, this and this will cancel, this and this will cancel. So it will be x square minus 2. Okay, so this will be x square minus 2. So therefore I can write it is d square y by dx square minus y plus x square minus 2 is equal to 0. So this is the desired differential equation. Okay, now coming to the solution of 2. What is my y dash? Y dash is 3a e to the power 3x plus 5b e to the power 5x, and I need to differentiate twice because 2 constants are involved. So y double dash will be 9a e to the power 3x plus 25b e to the power 5x. Okay, so this implies I can simplify it like this. So now just bringing this y to this side, y dash to this side, I have this and this. Now I eliminate y dash and y double dash. Let it be my 1, let it be my 2, let it be my 3. Now eliminating a and b within I, 2i and 3i, we get the coefficient of a is e to the power 3x, coefficient of b is e to the power 5x, and it is minus y as a constant I will take here. So similarly the second, it is 3 e to the power 3x plus 5 e to the power 5x minus y dash, and from the third equation it is 9 e to the power 3x, it is 25 e to the power 5x, it is my y double dash. This determinant value is equal to 0. If I take common e to the power 3x and e to the power 5x, then it will give me 1 minus y. From this I take common e to the power 3x, then it is 3, this is 9, and this is here 5 e to the power 5x taken common, this is my 25, and this is my minus y dash minus y double dash. If I multiply it Okay, now taking this to right hand side, it is 0. So now just evaluating this determinant, I will get 30y minus 16y dash plus 2y double dash is equal to 0, or simplifying y double dash minus 8y dash plus 15y is equal to 0. So which is the desired differential equation. Now to summarize, in this lecture we have discussed, first I have discussed the background of this lecture and what is the justification to learn the differential equation, what I call the introduction. So then the basic definitions. In the basic definitions we know what is the solution of a differential equations, what is the general solution, what is the particular solutions, what is ODE, what is PDE, so on, and finally we know what is a singular solution, right? Then initial value problem, boundary value problem. So these are the things we have discussed. Now coming to the formulation of the differential equation, as many as arbitrary constants, the final differential equation will be of that order. Okay, now coming to the upcoming lecture. In our upcoming lecture we will discuss the solution of first order and first degree differential equation. There are different methods like your variable separation method, homogeneous, bringing to homogeneous form, then your exact differential equation, then your integrating factor, linear differential equation, etc. So these are the methods to solve the differential equations, which I will discuss in the upcoming lecture. Now my appeal to all of you, if this lecture is helpful for you and you feel it is interesting, please like and subscribe to this channel, which will boost my motivation to prepare further lectures for your benefits. Thank you all. Have a nice day.